At CryoNox, our concept focuses on the refinement stage of lunar fuel extraction, specifically addressing how icy regolith is processed within permanently shadowed craters on the Moon. Introducing the refinement stage of CryoNox's lunar ISRU. The extraction cycle begins as icy regolith is delivered into a sealed processing chamber. The chamber is naturally maintained at a low pressure, closely matching the lunar vacuum. Electrical heating elements are activated, raising the temperature of the material above the sublimation point of water rise. The ice transitions directly from a solid to a vapor, with no liquid phase being formed. Throughout this step, the regolith itself remains fully solid. Vapor flow is driven by a thermal gradient from the warm sublimation chamber to a colder downstream region. Once sublimation is complete, the remaining dry regolith settles naturally at the base of the chamber. A piston press engages, compacting the loose material into a dense regolith puck. This compaction requires relatively low force due to the angular grain structure of lunar soil. The press mechanism is isolated from the vapor flow path, operates in discrete batches, and is designed to be robust and tolerant of wear. Following compaction, the regolith is aligned with an exit port. A one-way extrusion tunnel is used, incorporating a spring-loaded flap that prevents backflow into the chamber. The piston advances, ejecting the compacted puck onto the lunar surface. The system then immediately resets and begins the next cycle autonomously. Meanwhile, the water vapor produced during sublimation exits the chamber through an upper port and enters a vapor dust management system. Initially, a coarse mesh blocks any large debris particles. The gas then passes through a series of angled baffles. As the vapor follows the sharp turns, residual dust particles impact the baffle walls, lose their momentum, and adhere electrostatically to the walls. No fine filters are used, eliminating any clogging which may occur during the process. During periodic cleaning cycles using cold gas flushing, accumulated dust falls back into the chamber for later compaction and removal. The clean vapor then moves passively through ducts towards the next chamber, where condensation occurs in a cold trap consisting of radiatively cooled plates. These plates are permanently shadowed from sunlight, allowing them to remain at cryogenic temperatures at all times. When the vapor contacts the plates, it freezes directly into clean ice. Ice accumulates gradually, with sensors continuously monitoring its thickness. When sufficient ice has accumulated, the cold plates are gently heated. The ice transitions from solid to liquid water, which drains under gravity through guided channels into a sealed storage tank. Sensors monitor water volume, and the tank functions as a buffer between extraction and later processing. Stored water is then routed into a filtration system housed within a rotating drum assembly. The drum contains multiple filter cartridges arranged in sequence. When a cartridge becomes too clogged, the drum rotates automatically, aligning a fresh cartridge into the flow path. Self-sealing valves isolate spent filters, allowing continued operation without intervention. The system is fully enclosed, allowing for gradual degradation over time. Finally, the filtered water enters the electrolysis chamber along an added electrolyte, where a DC current splits it into hydrogen and oxygen. The gases are separated immediately into independent plumbing systems, dried and purified. Cryocoolers then liquefy the hydrogen and oxygen, producing both liquid hydrogen and liquid oxygen. These propellants are stored in radiatively cooled vacuum-insulated tanks, ensuring safe storage until transfer. At this point, the fuel is fully refined and ready for transfer, enabling cheaper, more reliable development of the cislunar industry.